Everybody, welcome back. We're going to go ahead and get started with a refresh your understanding. Okay, hopefully everyone had a chance to think about this a little bit more. So let's go through the answers. The first one is true. So if you are trying to evaluate the value of, this is in the tabular case, so this is where we're assuming we're going to sample each tuple at random, and then we do a Q-learning update. We do this an infinite amount of times. We know for standard tabular learning, we can converge to the true value of a policy as long as our learning rate schedule is such. So if exists a learning rate schedule if you're decaying your learning rate at the right level, then you will converge to the true Q value in the tabular case, because there's no function approximation that's happening there. In the second case, this is also true. So we talked a bit about how we could think about doing these things in a batch way, where we do it over and over and over again. We take our existing data and we run it through our either TD learning update or our SARSAR update or other things. And we said that the TD learning updates, if you do it in a batch way, are equivalent to just taking a certainty equivalent model, which means you estimate the dynamics model and you estimate the reward model, from your existing data, and then you do dynamic programming. So that's what we saw. I think we saw that in lecture 3. This one is false. Does somebody want to say why it's false? This one is not true. There's a number of reasons why it could be false. Somebody want to share why? Why is DQN not guaranteed to necessarily converge to the optimal Q function? Yeah, remind me your name.
Would you need to enforce a certain number of iterations for it to have any chance of converging at all?
It's a good point. So it relates to that. So certainly if you don't do enough iterations, but even if you do an infinite number of iterations, it also might not be guaranteed to converge. Tell me why, even with infinite. So you certainly need a lot of iterations, but even if you got a lot of iterations, you still might not be guaranteed to converge. I think here it helps to think about what we often call realizability, which is we don't know what the functional form is of Q. And so you could think of the fact that I'm going to draw it in as if the state space was one-dimensional, but in general, of course, like the state space is like this vector, or it's like, images, and so it's really high-dimensional. But imagine that it was one-dimensional. Even here, you don't know what your V function or your Q function might look like. And so if you are using the wrong approximator, like if you are using, say, a line instead of a multi-degree polynomial, then no matter how much data you have, you're not going to converge to the optimal Q function. We will be guaranteed that you will, because you just can't even realize it. So in general, and there's all sorts of additional instability things that mean we can't be guaranteed it's going to converge. So we're not guaranteed it'll converge, but empirically it often does pretty well. So we'll see. If you look at the empirical results, it often does really quite well. Great. So far in the class, we've talked a lot about these value function-based methods where we thought about having an explicit representation of the expected sum of discounted rewards starting in a state or starting in a particular state in action. And so we talked a lot about value functions and Q functions. And now we're going to talk a lot about policy search. And so we're going to still think about there being this policy, which is a mapping of states to actions, or a mapping from states and actions to a number between 0 and 1, such that it sums to 1. So we always have to do at least one action in every state. But we don't necessarily have to have an explicit representation of the value function anymore. So these have been very popular and important. And if we think back to what our algorithms involve, they involve optimization, delayed consequences, exploration, and generalization. And we've seen examples of all of these ideas so far, and we'll go a lot more into some of them as we go through the course. But one thing you might be wondering about is, could we play the trick that's often done in computer science and try to reduce reinforcement learning to another problem. So could we do something like just like online optimization? So we know that we don't know how the world works and we're trying to find a good control policy, but could we do something like sort of online optimization where we're trying to search for a good policy? And in this way, you can think of policy gradient being related at a high level to this type of idea. It's not a reduction-based approach, but it's sort of thinking about sort of, well, can we just directly search to find a good policy? And policy gradient methods have been extremely influential, particularly over the last 5 to 10 years. So they're used for lots of areas. They're used for things like, sequence level training with recurrent neural networks. That was based on Reinforce, which is an algorithm we're going to go through today. It has been used for things of end-to-end training of deep visuomodal policies. So this was really influential work in the robotics community about a decade ago. I'm just going to show you a quick video of it. So this is work that was done by Professor Chelsea Finn as part of her PhD thesis, along with Sergey Levine and others at Berkeley. Let's see if this will work with audio. So what you can see there, that what they're doing is what they're going to be trying to do is learn from, so they showed you they showed a big network. And what they're trying to do is go directly from pixels to learn what the robot should do. And this is one of the first examples of people trying to do this directly from images. Let's just go back to some of the tasks that they're using. And so that was part of the motivation too, is that they want to be able to learn these tasks in a way that will generalize. So this is another example of sort of trying to do direct policy gradient methods in order to go from really large, complex state spaces into direct decisions. Now, in homework 2, and we haven't covered PPO yet, but you're going to be implementing proximal policy optimization, which is one of the methods that build on the sort of methods that we're going to talk about today. And that was used, PPO was used as part of training ChatGPT. So as you can see, all of these algorithms have become incredibly influential, in part because they can scale really well to extremely complex inputs, whether it be images or high-dimensional robotic tasks, or even things like natural language. And so they're very powerful. They're often used in conjunction with things like state action values, as we'll talk about later, but you don't have to use them with them. So they're a really useful sort of class of things to know about. So in particular, just like how last time we saw that you could approximate a state action value or a value function with a set of parameters, so we can do function approximation. In those cases, we thought of directly learning a value function or a state action value function, and then it generate a policy from the state action value. So something like eGreedy, where we either take what the Q value suggests is the best action, or we act randomly. And what we're going to do today instead, and I'll try to be careful about not using the same, we use W before to parameterize our state action values, and I'm going to try to be careful about using theta, just to make it clear. We're going to directly parameterize the policy, and we're going to try to learn parameterized policies. So we could think of these as deep convolutional neural networks, which at the end will output either an action, or if we have an action as input, will output a probability. And the goal in this case, as is normal, is that we want to find a way to act in the world that will give us high reward. So we want to find a policy with the highest value function v pi. And we're again not going to be focusing on model-based learning. So we're sort of going to try to directly learn from experience. We're not going to assume we have access or that we're explicitly building a model. And I think one of the things that's helpful to think about is there's these sort of different views or lenses into reinforcement learning. So this is a nice picture from David Silver, who's an amazing person in reinforcement learning. He was one of the main leads on AlphaGo and a number of other incredible papers. So you can think of it as like you have some methods which are value-based. We're explicitly building a value function. We have other ones that are policy-based. And the ones that are in the intersection are often known as actor-critic methods. Who here has either implemented or heard of actor-critic methods before? Okay, so some people, not everyone, they're extremely popular. And in actor-critic methods, you will often combine between the benefits of value-based and policy. And so, for example, AlphaGo is a actor-critic method in the sense that it is often having explicit representation of the policy and of a value function. Okay, so we'll get to actor-critic methods later. Today we're going to focus on policy-based. So now that we're going to, most of the time we've thought about policies so far, we thought about deterministic policies or e-greedy policies. And now we're going to think much more generally about stochastic policies. And that's going to be important because, as we saw last time, if you only have a deterministic policy, it's much harder to learn about actions you don't try. Whereas now we're going to think about having stochastic policies where you're going to be getting information about lots of different actions. So let's think about a particular example, also to kind of illustrate some of the things that policy gradient methods are going to help us handle. So who here has played rock, paper, scissors? Okay, most people. I think it's called Rochambeau in Chinese. It's a very popular game throughout the world. It's a stochastic game where, each side can pick a particular strategy, and the state, you could think of there being a state, you could keep track of what your opponent has done over time. So think for a second about whether a deterministic policy can be optimal if you're playing this game repeatedly. So raise your hand if a deterministic policy can be optimal. Raise your hand if you think a stochastic policy is optimal. Okay, someone who said stochastic, explain why. Yes.
Because, I guess moving to is circular. There's no one best one that beats everybody.
That's right. Yeah. So there's no best. There's nothing that strictly dominates all the other strategies. And also, if you're deterministic, what can your opponent do? If I say I'm always going to pick paper, what does my opponent do? They're always going to pick the other one, rock to beat me. So anything you do that's deterministic can be exploited by your opponent if you are playing repeatedly. And so the optimal thing to do here is to be stochastic. So the optimal policy has to be stochastic here. Otherwise, all deterministic policies are strictly dominated by a good stochastic policy. Okay, and now you might think, well, all right, well, that sounds different than what we've seen so far, but one of the challenges here is the system is not Markov. So it's not stochastic what your adversary will play next. They're not random, or it might be if they're playing a stochastic policy, excuse me, but in general, they can react to what you've seen so far, and it's not just a random environment like a coin flip on the next time. And in this case, actually, a uniform random policy is optimal. It's the Nash equilibrium. Okay, so that's one case where having a stochastic policy would be really helpful. So you could just have a fixed stochastic policy and it would be optimal, but you couldn't necessarily write this down easily as a Q function and just take the argmax. There's not a deterministic policy for this environment that is optimal. And so it's less clear how you would write that down directly in terms of a Q function, in part because the system is not Markov. So here's another example where we might want to have stochastic policies, and it's where we have aliasing or partial observability. So imagine this case where you have a robot that's walking along and maybe they have sensors so they can tell how far they are from the walls, but under those sensors, these two gray boxes look identical. Because from the agent's point of view, if they have only immediate sensors, both of those places will look identical. And so they can't distinguish those gray states. And imagine that, you just, because you have a feature representation that just tells you about whether you have a wall to the north, to the east, to the south, or to the west. So those two gray states would look identical if that was your feature representation. So you could have a value-based reinforcement learning representation where you use an approximate value function, where you take in this as the state representation, or you could have a policy-based one that takes in those. So the challenge here is that if you're value-based, you have to do the same thing in those two gray states because you can't distinguish them. So from your perspective, it's like you're in the same place, no matter which of those two places you're in. And so if you're going to do a value function based and then extract a deterministic policy, you would either always have to go, say, to the left in those cases, or always go to the right. And neither of those would always be good. Okay. So under aliasing, meaning that we don't know which of the two gray states we're in when we're in one of them, an optimal deterministic policy will always move west in both states or east in both states. And either way, it might get stuck and never be able to reach the money. But and that's what's going to happen if we do a value-based reinforcement learning approach. So that's not great. You're going to traverse this for a long time. You're not going to be getting high reward. What could you do if you wanted to have a stochastic policy? So that allows you to act randomly or stochastically at any state. What do you think would be the right thing to do in the gray states if you could have a stochastic policy?
With 50% probability, you go either east or west.
Yeah, exactly. So exactly what I said. So you could just randomize it. So an optimal stochastic policy will randomly move east or west in the gray state because it doesn't know which one it's in. And half the time, that'll be the right thing to do. So sometimes that means much more of the time it'll go into here. And it generally will reach the goal state pretty quickly. So this is another case where the system is not Markov. This is not Markov in the state features. So because we have aliasing, meaning the system is partially observable, it is not a Markov system. One way to handle that is to treat it as a partially observable Markov decision process. Michael Kockendeffer talks a lot about those in his classes. But an alternative is to use a stochastic policy. And you can also act very well here. So those are two examples of sort of the type of thing that might be able to be easy to handle with policy gradient methods or stochastic policies that might be hard to tackle with the type of methods we've seen so far. Okay, so now we have to think about if we have policies, and in general we're going to want them to be stochastic, how are we going to learn what are good policies? Like we have this, now we have a function space over policies, and we want to learn which of them have good values. So if we're in an episodic environment, we can use the policy value at the start state. So we can just say, I'm going to, similar to the Monte Carlo methods, if I start in this state, I run this policy, what would be my expected reward be until the end of the episode? We're going to mostly focus on the episodic case today, but you can extend these to sort of more of an infinite horizon case. All right, so once we think of it in this way, we can really think, okay, this sounds like an optimization problem. So we really just want to find the parameters that maximize the value. So you could say, here you can think of this as being your thetas. So I'm just drawing it in one dimensional, but in general, this could be all the parameters in a deep neural network. And then this is v of theta, or of a particular starting state. It might look like this. And what your goal would be is to find the parameters of your policy that maximize the value function. And so this is an optimization problem, but it's a hard optimization problem because we don't have that function. You can only estimate it through data. And so you can imagine, like, you start off, you have no idea how theta maps to v, and then you have to learn that over time. So once we think of it as an optimization problem, where we don't know what the function is, there are a lot of different methods we could think about to try to solve this problem. And what we're going to focus on today mostly is ones that are going to exploit something about the structure of sequential decision processes. But there are methods that completely ignore kind of all of this. And in particular, you can even use things that completely ignore gradients. So you can do things like hill climbing or genetic algorithms or cross-entropy methods, where you may not think of sort of any of the type of structure of the parameter space. And in some cases, that can work really well. So there's a really nice example by my colleague Stephen Collins, who's over in the mechanical engineering department. He does some really interesting work on, oh yeah.
Are you inducing randomness from outside the network? Because for any configuration of theta, the order function should be deterministic, right?
Yes, but you can make it a distribution over actions. So you can output something between 0 and 1, and you can have an input action, and so then you would have a stochastic policy.
But if something would be still outside the network.
You would then compute that for all of the actions. Then you would have to have you'd have to pick a random number and then use that to select them. Yeah, good question. So my colleagues, Stephen Collings over at Mechanical Engineering does a lot of work on exoskeletons. And there are lots of reasons exoskeletons could be really helpful, particularly for people that have motor impairments. But one of the challenges of them is that you have to have them actually help people walk. So if you clamp something onto, say, your leg, then the way my physical configuration is may not be the same as your physical configuration. I'm pretty tall. And so you'd really like to make sure that this helps each individual in the best way possible. But you don't want it to have to learn over the course of 2 years how to best optimize to someone, because they're not going to wait that long to use it. So what they did is they used policy search methods, to quickly personalize the parameters of an exoskeleton. And they called this human-in-the-loop exoskeleton optimization. So the idea in this case is what they're trying to figure out is what is the parameters of their exoskeleton. And what they're looking at is essentially how much it helps you walk. So how much it reduces the effort needed to walk. And so what they could do in this case, they're not using like a gradient-based method, they're using just CMAES, which is, so the treating is sort of continuous optimization, is they'd have people walk under sort of a few different control parameters. They would see which of those seem to be most effective, and then they would move the policies they'd try in that direction with some stochasticity. And I think it was within maybe 2 or 3 hours using this, they could find substantially better policies. I think it increased metabolic efficiency like maybe by 20% or 30%. It was pretty remarkable. And so this was published in Science about 7-8 years ago. But that's another example of a place where you can do this sort of like online optimization, but you don't necessarily have to think about the temporal structure of the policy. Yeah?
So in this example, do we start with a default policy and then try to improve that default policy?
Great question. Yeah, so in all of these cases, we're going to have to assume that we initialize our policy parameterization in some way. Just like how we initialized our value function to 0 to start, now we're going to, or if you had it for the deep Q network, it would be whatever your neural network parameters were. Yeah, great question. Now, it's just useful to know about these because they often work pretty well. So I think sometimes we like to leverage the structure specific to, say, our Markov decision process, but in some cases, just leveraging these ones which may not use very much structure at all can actually do really well. So it's just good to keep in mind that there are a lot of ways to do online optimization. All right, so this is often a great baseline to try. The great thing about this is it can work with any policy parameterizations, even if it's not differentiable, because it's not using gradients, so it doesn't need to be differential. And it's also often very easy to parallelize. So CMAES, for those of you who haven't seen it before, you'll have a number of different policies you kind of try in parallel, and then you'll use that to sort of update and shift to another set of policies. And that's what they did, Professor Collings did. And in a lot of cases, the problems that we think about are places where you'll have many customers, you'll have many robot arms, and so you can parallelize things. One of the limitations is that it's often less data efficient because it's ignoring the temporal structure. So if you have temporal structure, or if you have a gradient information, it may be more effective to use that. All right. So what we're going to focus on in this class is differentiable methods. So we're going to focus on places where we can do stochastic gradient descent, including on the policy parameterization. So if we have like our policy parameterized by a deep neural network, we can propagate through that and update those parameters. So we're gonna focus here mostly on methods that do use gradient descent and that often leverage the sequential structure of that we're making a sequence of decisions and we want to optimize to make those sequence of decisions. So to do that, we're going to explicitly define the gradient, and we're going to write down the value function in terms of as a function of the policy parameters, so that we can be clear that this value function relies on those policies. And we're going to focus today on episodic Markov decision processes, where we go for a single episode, stop, reset, and keep going. All right. So now what we're going to do is we're only going to be trying to get, in general, to a local maximum. Now it's possible you're lucky and you're sort of convex in the space of the value, in space of the policy parameters, but in general, we're not going to assume convexity. So at best, we're going to hope to just get to some sort of local maxima in our space. So if we have, again, if we only had one parameter and we have something like this, we might get to here, we might get to here. In general, we're not going to make global optimality guarantees. This is in big contrast to the tabular cases we saw before. We were guaranteed to get to the optimal Q function, an optimal value function. Now we're just going to hope to, given our policy parameterization, let's try to get to what's a local optima in that policy parameterization. So it's sort of a policy-specific, policy class-specific guarantee, and it's only a local optima. And what we'll be doing is we're just going to be trying to sort of take the gradient of the policy with respect to the parameters. Okay? And as usual, we're going to have a step size parameter. So we're going to sort of take the gradient of the value function with respect to the parameters and take a small step. And the key thing is going to be thinking about places where we can do this all directly using sort of smooth functions. Now, one way you could do this, of course, but when you see this now, you probably immediately think of auto-diff methods and think about we can just backpropagate, etc. But it's worth noting that when these methods began to start to get popular, they didn't necessarily have auto-diff yet. I know there was research then still. And one of the things people started thinking about for this is how you could use this for robotics. So this is a nice paper from 2004, so 20 years ago, by Peter Stone's group. It was right around then, I think maybe RoboCop was maybe 6 years old then or something. I think they started it back in 1998 or so. So they're these little quadruped robots, and the goal was to think about getting robotics to the stage where you could have robots play human players. I think that was the goal by either 2030 or 2050, I forget. But what they were going to start with, it was quadrupeds. So one of the big challenges at the beginning, because everywhere you start with the beginning challenges and you go from there, is just getting them to walk fast enough. So if they're going to score goals and they're going to compete, you need them to walk quickly. And so there's this question of just how do you learn fast walks, so that they can sort of trying to teach robots to run. And what they found here is that they could use policy methods, policy search methods, just to learn a faster way for it to walk. And so they parameterized sort of the curve of how the foot moves as a set of parameters, and that defined the policy for moving those joints. And then what they did is they just had these walk back and forth many, many times. And what they would do is they'd have them walk, with some particular policy parameters. They would see how fast they walked. They would do finite different methods. So they weren't trying to explicitly do auto-diff or anything there. And then they would slightly change the policy parameters and repeat. And they learned a substantially faster walk during that. And I think it took maybe around 4 hours or so, but they just had to replace the batteries a couple times. So it's just an example to say, it's lovely to have auto-diff. You can do really complicated things now, but these methods can work even in really basic settings, particularly where you think you have pretty bad models of how the world works. And so now you can just be directly data-driven. And why is this a hard problem? For those of you that haven't done robotics, it involves a whole bunch of contact forces. The ground may be, they have to learn on this particular ground. You may not know because it's commercial hardware. You may not know exactly all the parameters that the designers put in. And so you can just be data-driven, okay, as opposed to maybe having a physics simulator. All right, so just to summarize so far, the benefits of policy-based RL is that we're going to have often better convergence properties. We're often going to be able to guarantee that we get to a local optima, whereas we didn't have that for deep Q learning. They're often really effective in high-dimensional or continuous action spaces, and you can learn stochastic policies. But the methods we've seen so far might be more inefficient and higher variance, and we often only get to something of a local optima. And we'll see some things to help with kind of the inefficiency in a second. All right, so now what we're going to dive into is how do we do this when we are willing to have differentiable policies. So the hope is that we can actually compute the policy gradient analytically. So we don't have to do it with finite differences. And we're going to focus on policies where it's differentiable as long as it's non-zero. So we're going to assume that we can always compute the gradient of the policy parameters themselves. And there are a number of different classes we can do this for, and there are many popular classes, including, of course, deep neural networks. So popular ones are often softmax. Softmax is used all the time. I'll explain what it is in a second. Gaussian, and neural networks. And again, just to be clear here, what I mean by a policy class is what is the functional form we're using to give us a probability of an action given a state. So are we having something like, well, I guess we can just see on the next slide what these will look like. Okay. So we're going to assume, I'm going to give you some examples of those, of what softmax and Gaussian and neural networks look like in a second in terms of how we differentiate them. But these are just different ways for us to parameterize what is the probability of an action given a state. Actually, I guess I'll give a quick example with Gaussian. For Gaussian, you could imagine, let's imagine I have a robot and I'm trying to figure out, say, how much speed to apply. Then you might have a policy class that says the action I take is equal to a Gaussian centered around 0.5 with some standard deviation. So it would be a stochastic policy. And it would say the average amount of speed you're going to apply is 0.5, but you're going to have some variability around that. And that would give you some stochastic behavior. So sometimes your robot would go really slowly, sometimes it would go fast. Sometimes it would go in a negative direction. Okay, so let's keep assuming that the policy is differentiable. Whenever it's non-zero, we know the gradient. That still doesn't tell us how to solve policy gradient methods yet, because what we want to do is take derivatives of the value function. So we want to say, I want to find the maximum, the policy that has the best value function, which means I'm going to need to take the derivative of the value function with respect to the policy parameters. Okay. So remember that the policy value, the value of the initial starting state under a policy, is going to be the expected sum of rewards. We don't have to use discounting for most of today if we assume it's finite. So I'll just say, we're going to assume we're in the episodic case. And so this is finite, so no discounting for now. So we don't need discounting for now because it's always a finite length, so we're never going to have infinite reward. So the policy value is just the expected sum of discounted rewards when we follow the policy parameterized by theta till the end of the episode, starting from the state S0. And there are lots of different ways for us to write this down. So one way is for us to write down V of SR is equal to, well, it's equal to the state action value averaged over the probability of us taking each of those actions under our policy. So this here just says, what is the probability of me taking this action, starting state S0, if I have policy parameterized by theta, times what is my Q value of starting that state, taking that particular action, and then following that policy for the rest of it. Okay, so this is one way to write it, but we can also think of a quite different way, which is, let's think about trajectories. I'll write down what these are in a second. Okay, so this is a trajectory. What's a trajectory? That's going to be S0, and then it's going to be an action, and then an S1, ... sampled from pi theta. Okay. So another way we can think of the value, and then this is going to be the reward for that trajectory, that whole trajectory. And we've called RG before, so sometimes I'll just write down that in case. Sometimes SG. So another way we can think of the value is we say, well, let's just sum over all possible trajectories we could reach under this policy, and what would be the reward for each of those trajectories. And I'm just going to take a weighted sum. Now, of course, you might be thinking that's totally intractable, and yes, in general, if you have a really long trajectory, then it's going to be intractable, and you have a really large state space, and you could reach many states. In general, it's not going to be possible to actually enumerate this. But this is mathematically well defined. This is just an expectation over the reward of trajectories. And we know whenever we see expectations that we can approximate those with finite samples. You can think of just taking n samples, just like what we saw with Monte Carlo methods, and using that to approximate a trajectory. So in general, this is intractable. General, intractable. But we can approximate by sampling. All right. So this is one way we could write down. So this is another also valid way to write down what is the value of starting this state and following the policy. Okay, so I've written that down more neatly here. P of tau theta is the probability over trajectories when you execute that policy starting state S0, and that is the sum of the rewards for a trajectory. In this class, we're going to focus on this latter definition, but inside of Set and Bardo, they have a nice way to think about policy gradient methods that starts from the other definition. So you can always look at that. But both are totally valid definitions. All right. So now we're going to focus on thinking about likelihood ratio policies. So we're going to be thinking about this case where we have a distribution over trajectories, and then what is the sum of rewards for each of those trajectories. So we have our value function. And now what we want to do is find the argmax so that we maximize us having a probability of getting trajectories with high reward. So that's nice. So instead of just thinking about the value function, we now can think of it as, okay, I want to have policies that induce trajectories through the state space, through the state and action space, that give me high reward. So what we're going to need to be able to do is to take a gradient through the right-hand side. Okay, so that's what we're going to do now. Okay, so we're going to take the gradient of this, because once we have the gradient of the value function with respect to the policy parameters, we can update our policy parameters to increase, hopefully, the value of the policy that we're at. Okay. So what we're going to do is we're going to say we're going to take the gradient with respect to the right-hand side. We can rewrite this by pushing in the gradient. Okay. Now, R of tau doesn't depend on the policy parameters. That's just what is the reward once you've told me what a trajectory is. So we can put that on the other side. This is the only part that depends on the policy parameters. And now I'm going to play a trick. I'm going to note that this is going to be equal to, well, I'm going to do something that's going to seem not very helpful for a second, and then we'll see why it's helpful. I'm just going to multiply and divide by the probability of a trajectory. Okay. I haven't done anything. I've just multiplied by 1, and I've happened to multiply by the top and bottom by the probability of that trajectory. But then I'm going to note that the derivative with respect to log of the trajectory in theta is just equal to 1 over the probability of trajectory in theta times the derivative with respect to the trajectory in theta. Okay, because the derivative of a log is just equal to 1 over the value times the derivative of the thing inside the log. So that looks exactly like this. Okay, so that's the trick that we're playing here. And so we can rewrite this then as the probability. And I'll tell you why we did this in a second. Okay. All right, and let me just rewrite it one more time so it's kind of more easy to see. Why did we do this? Okay, the reason we did this is that in general it's going to be hard for us to think about, or it might be tricky for us to think about how do we propagate our derivative through something that's an expectation. We had an expectation over all the trajectories weighted by the reward of those trajectories. We now want to take a gradient with respect to it. We want to end up with something that is computable from samples, because it's easy for us to get samples. We can actually run our policy in the environment. So by playing this trick, what we now have is something that we can also sample. Because this is now an expectation over trajectories of the reward of the trajectory weighted by the gradient of the log of the probability of that trajectory. Okay, and we'll talk soon about how you compute this part, but this expectation can be sampled. Okay, because this is just a probability over trajectories. And so we could sample, say, 100 of them and approximate that outer expectation. So that's one of the reasons why this is, I'm just writing this out more neatly here on the next slide. This is called the likelihood ratio, this term here. And so that's one of the benefits to doing this, is that we want to end up with something that is computable. We want to be able to get this gradient with respect to the value function for the policy parameters. And so this is going to give us something that we can approximate with samples and we can compute. Okay. All right. Now you still might be a little bit concerned because, all right, maybe you think, yeah, I can maybe compute this by like writing things out in the environment, but I'm still going to have to take this derivative. And how am I going to do that? And what does it end up depending on? So let's do a next step. So as I said, what we're going to do here, this is an expectation. And we're going to approximate that expectation with an empirical estimate. Okay, so we're just going to, instead of actually taking, all possible trajectories, particularly in the case of vision input, you could imagine that would be completely insane. So we're just going to approximate it by taking m samples. But we still have to handle this. Okay, so that's what we're going to do next. So this first part should all seem clear. The second part should, at least certainly for most of us, would not be clear yet about how we do that second part. Okay, so what do we do with that? What we're going to do now is we're going to decompose that latter part into states and actions. So remember that what this means here is this is going to be a particular trajectory we get by following a policy for t steps, or until the end of the episode. Okay, so let me just remind ourselves what t is going to look like here. So this is going to be like time step here. I'm using the subscript as time step. Okay, so let's just write out what a trajectory is and what those probabilities are.
Are we approximating the probability of the trajectory just to be 1 over m?
No, good question. Yeah, sorry. Yes, for this part, yes. We're assuming that we're for each of the trajectories, we're using like a Monte Carlo estimate. We're just using 1 over m. But if some trajectories are more likely than others, they'll appear more in that set of m. That's a good question. Okay, so let's now try to express what the probability is of a trajectory. Okay, so the probability of a trajectory we can write out as follows. So we're going to still have that outside log. We're going to do the following. Okay. I'm going to say mu of S naught is equal to the probability of S naught. Okay, that's just like what is our probability distribution over our starting state. Okay, so that's mu. And then what we're going to have is the following. T equals 0 to t minus 1. We're going to have our policy. So this is going to say, what is the probability that I pick the action I picked, given the current state I'm in, times the probability of st plus 1 given s0 to t, a0 to t. So what I've done is I've just written out what is happening in my trajectory here. Is I have some distribution over c in this initial state. Under my policy, I have some probability of taking a0, and that's here. Then I'm going to assume for a second that rewards are deterministic, but you could add in a reward term here. And then I'm going to say, well, what's the chance that I get to state S1 given my history, given the previous states and the actions? So I've just written this out as a joint probability. Okay. And now what I can do is I can use the fact that log of a times b is equal to log of a plus log of b. So I'm just going to decompose all these terms. Okay, so I'm not applying my gradient yet. But I'm just going to have log of mu of s naught plus sum over t equals 0 to t minus 1 plus t plus sum over t equals 0 to t minus 1. Oh, let me put the log in. Sorry, it's a bit messy. I'll make sure to add a clean version. So what I've done is I've just decomposed my log, but now this is really nice because this term is not a function of theta. This is just my initial starting state distribution. It has nothing to do with my policy, so this drops out. Does this part depend on my policy? Yes. Does this part depend on my policy? No. So when we take the derivative of it, it disappears. So that is beautiful because now it means we don't have to know about our dynamics model. Okay? So the only term that is still around after this is this thing. All right. So this is great because now we don't depend on our dynamics model. We have written down what this term is as a function of, so we're just doing this term right now as just the sum of the derivative of the log of the policy at that particular point. So we're sort of summing up for each of the different actions we took along the way, what was the log of their probability, and taking the derivative of that whole term. All right. So we don't need any dynamics model, which is great. And I'm just going to say here, I'm going to make sure that something is consistent here. Oh, yeah.
I had a question on the slide.
With all the math. Uh-huh.
So in the dynamics model, the PS at t plus 1, for the given part, why do we look at the entire history and not just the past state in action?
Great question. So what I've written out, so this question is a good one. I wrote down here the dynamics in a really general form. I am writing them down and I'm not making the Markov assumption. We could make the Markov assumption, but what I wanted to point out here is that you don't have to make the Markov assumption. It does not matter. So because the dynamics model are independent of your policy, when you take the derivative, they completely drop out, whether they are Markov, whether they are non-Markov, etc. And so that's really nice. It shows that in this case, it's not making the Markov assumption. Now, I did make the Markov assumption somewhere. I made it here, because I assumed that I made the Markov assumption in the sense I assumed my policy was Markov. My policy is only depending on the current state, but your policy also could depend on a history of states. You know, you could have like a recurrent neural network or any of the other representations you might want to choose there, and you would still, then this would just depend on your history. Good question. All right, so I just want to go, and I want to make sure that I wrote it down neatly in terms of the most general form. That's why I'm skipping those right now. One of the things to note here in terms of just notation is that people often call this thing here a score function. So this derivative with respect to log of the policy itself, we often call a score function. Okay. So in general, the nice thing is that it's generally not very hard to compute the score function. So if you have a differentiable function, we can compute the score function pretty easily in many cases. Let me just make this a bit smaller. Okay. So let's see what that might look like for a couple different policy classes. So one thing we could do, which is a pretty popular thing to do, is to do a softmax policy. So the idea in this case is that let's take a linear combination of features, so 5SA dot product with theta. And then you could say the probability of your action is proportional to the exponentiated weight. So you take the exponent of that dot product between the features, and then you normalize it. And that gives you generally a stochastic policy. You can also have a temperature parameter in there if you want. Okay. And the nice thing about this is that we can write it, we can take the derivative of this very easily. Okay, so we can just do that quickly here just to illustrate. So what this is And this is just to illustrate that like it is often very feasible to take the derivative with respect to the policy parameterization. Okay, so this is just going to be the derivative of the log of e to phi of SA t theta divided by phi SA. Okay. So we can do this here, and we can rewrite this here as and so this is just going to be equal to phi of SA minus 1. So I'm just taking the derivative of this for a particular theta. And so we can just rewrite that as phi of SA minus some theta. Okay, so what I've done here is I've taken the derivative with respect to this function for a particular theta. And then what I've said here is, well, you could notice that this here is exactly just equal to my pi theta of SA. So it's like I'm getting this weighting over the features. Okay, I'll put this on the next slide neatly. Okay, so the score function for the softmax policy is just going to be equal to the feature SA, phi SA, minus the expected value over the policy of the features. Oh, great question. Well, phi could be, for example, you could think of it as like if you have a large neural network that's doing some representation, it could be the last layer, like the second to last layer. And then you could just do like a linear dot product of that. Yeah, it's a good question. You could think, or in case of customers, it could be a whole bunch of different features. And then you got different weights of them. All right, so this is also possible to do for other functions. So for Gaussians, we often want to think about that for continuous action spaces, which are really useful for robotics, where you might have like continuous torques, or continuous accelerations, etc. You can think of there being a mean, which is a linear combination of some state features. Your variance might be fixed, or it could also be parameterized. And then your policy is a Gaussian. So like maybe you're sampling some particular action dependent on your state, along with some variance. And then you can, again, just directly compute what the score function would be in this case, in closed form. But in general, you're often probably going to be using this with deep neural networks, and then you can just use autodiff to do this. It's just to illustrate that there's a number of different functional forms where you can compute this analytically. Okay. All right, so just to recap this, what we've shown so far is that we can have policy methods where we have a direct parameterization of the policy. We can write down the value function as being a weighted sum over the trajectories generated by that policy times their reward. It turns out that when we want to take the derivative of that, we can re-express it so that we just think of, we don't need the dynamics model, and we're weighing these score functions. So now let's just do a small check your understanding about likelihood ratio score function policy gradients. And so what I'd like you to do is say, does it require that your reward function is differentiable? Can you only use it with Markov decision process? Is it useful mostly for infinite horizon tasks? A and B, A, B, and C, none of the above, or not sure. Let's just take a second to do that. All right. We have a good split of opinions. Nobody is not sure. But there is a lot of spread. So why don't you talk to your neighbor and see if we can come to more consensus. All right, I'm sorry to interrupt some good discussions, but I want to make sure we get through reinforce today. So So it's a little bit of a tricky one. In fact, when I was giving it to one of my TAs, I forgot to put the none of the above, and he was like, wait, what? So it's none of the above. And so the first one's part of the actual elegant aspect of policy gradients. So as you can see here, you need the policy function to be differentiable, but the reward function does not have to be. The reward function is not a function of the policy in the way that we've written it here. So that's pretty elegant. So that has motivated people in a really wide range of areas where you really might have very complicated reward functions to be interested in using what we're going to see soon, which is reinforce, which is based on this idea, because you just need the policy parameterization to be differentiable. So that's really cool. B doesn't have to be Markov, because as we saw, the dynamics model drops out, and so as I was just saying, in that case, it doesn't appear at all. So it doesn't need to be Markov, you don't need differentiability. We are assuming that it's finite horizon so that we can actually, episodic, so we can get n more than one. If it was infinite horizon, we'd only get n equals 1. So all three of these are false. So let me just make sure I circle that. Okay, so just to give brief intuitions, because to make sure that we get to reinforce, you can think of if this is a generic way of writing this down, we sort of have some function times the derivative of log of some other probability function. And you can think of this first part as measuring how good a sample is. And what the idea is that when you have the derivative, you're trying to sort of move up the log probability of samples that have high reward. Because you generally want policies that visit parts of the state and action space where you get high reward. So that's kind of the intuition. And the nice thing is that f doesn't have to be differentiable. It could be discontinuous. It could be unknown as long as you can get samples from it. So it can be extremely flexible to what is that reward or objective function. So I put a couple of slides here. I believe, I don't remember if it was John Schulman who originally had these ones. I put some credits at the front, but you can think of sort of taking a combination between what the probability is of your input of your x as well as your function. So in our case, that's going to be the reward function. This is generally going to be the reward function over trajectories, and this is going to be our policy. It gives us probabilities of the trajectories. And so you can think of combining between these two to actually change your parameter space. Just to give a little bit of intuition over what this sort of gradient estimation is doing. Okay. So in general, we can also write down a policy gradient theorem, which says we could either use something like episodic reward, or we could be trying to look at average reward per time step, or we could be trying to look at average value. And in all of these cases, we can end up writing something that looks really similar to the equation I showed you before, which is the derivative with respect to these value functions or something like a value function is going to look something like the derivative with this score function, the expected value over the trajectories you're going to get of the log of the parameters times the Q function or the return for that particular state action pair following the policy. Okay. And there's a nice derivation in Sutton and Bardo about that. At a high level, I think the useful thing to know here is just that we can extend it beyond just thinking of kind of like this sample of return. And we can think of there being Q functions. All right, now what I've shown you so far is something that is correct, and we can turn it into an algorithm, but it does not leverage much of the temporal structure. So what do I mean by that? So what we've written down here is a valid gradient. It's unbiased, but it can be very noisy. So we're estimating this by Monte Carlo method because we have these M samples, and as we know from Monte Carlo methods before, they are unbiased, but they can be very high variance. And so some of the ways to make this more practical, and what I mean by that is a better estimate of the gradient, and hopefully with less data, because ultimately we're going to have to be using this information to update our weights to try to get to a good policy. So we want this to be data efficient, is we can try to leverage the temporal structure, and we can also include baselines. So let's first see the temporal structure. So what we've done before is we've summed up all the rewards from a whole trajectory, and we've multiplied it by the sum of this score function for the whole trajectory. That's what we've done so far. We can instead think of it as, what if we have the gradient estimator for a single reward term? Okay. So this is just, for one time step. we can think of it for there, which is we have that single time step times the score function for the remaining time steps, or for the time steps up to that point. Okay. So it's like we just think of the partial trajectory until we got that reward. Okay. So we want to think about sort of the derivative of this. This is the reward we got at this time point. So instead of having this whole sum, we just think of, well, what is sort of the trajectory that we got up to that time point and all of their score functions. Okay. Does that make sense? Have anyone had any questions about that part? Okay, so this is like for a single time step, t prime. And so now what we can do is we can sum this over all time steps. So instead of having the sum of all rewards times this, we can say, well, we know that for one time step, it is equal to the expected value of the reward for that time step multiply times these score functions up to that point. So let's just rewrite it like that. Now we're just going to sum over the rewards we got for all time steps. Okay. All right. So now what we can do is we can do slight rearrangement. Okay. So what we can notice is that for each of the points, so you can think of it as I have, so this is t, 0, 1, 2, 3. And you can think of all of these sort of score functions I have at each time point. So the score function at time step 0 is going to appear for R0, R1, R2, R3, dot, dot, dot. Okay. So that's what I've just done here. I've said this first term is going to appear with a reward function of all of the subsequent time points. Okay, because that decision happened, and then we got a reward, and then we got a whole bunch of rewards later. On the first time step, it can affect the reward we get at time step 1 and all the future after that. Okay, so this term here, this score function, can influence the one that we get on time step 1 can influence time step 1 all the way out to the end of the episode. The one we get on time step 2 can influence time step 2 all the way out to the end of the episode. Okay. So essentially this is like saying my reward on time step 3 cannot be impacted by decisions I make on time step 4. Time only flows one way. So if we think about what those score functions were, and like we think of like the trajectories that were generated, they're a temporal structure. And so it means that we cannot have, if we change the policy parameters such that decisions in the future change, that can't affect my reward on earlier time steps. Okay, so this is leveraging the temporal structure. So this just allows us to rewrite the equation so that now we have, for each of the different score functions, essentially which of the rewards they influence. And the reason this is important is because here you could see that we're multiplying each of the score functions by all of the rewards. And now we're only going to multiply them by the rewards they influence. And so in general, that's going to be way less than having the full set of rewards. So this is going to reduce the variance of our estimator without causing any bias. It's just leveraging the fact that decisions in the future can't affect your rewards in the past. Okay. All right. So that is one of the first things that we're going to do in this case. So we're going to write, so remember in this case that if we sum up all the rewards from the current time step to the end, we've just called that the return. We've seen that before from Monte Carlo. So we can just rewrite this expression like that. And that gives us the reinforced algorithm. So this is the reinforced algorithm that has been incredibly influential in NLP and robotics and many, many areas. Okay. And so what this says here is that the way we change our parameter is just our learning rate times our score function times the return we got from that time step till the end of the episode. So we still have to wait till the end of the episode to update anything. But what happens is we run a full episode with our current policy, and then for each time step, we slightly change our policy parameters by using a learning rate, the score function for that time step, plus the return we got from that time step till the end of the episode. And then we just step through that for the whole episode, and that's given us t different updates to our policy parameterization. And then we just repeat over and over and over again. And what that guarantees to us is that eventually we will land in a local optima of the value function for the policy parameterization. Okay. So this is called Monte Carlo policy gradient, or known as the reinforce. I believe this was in roughly 1992. It's about 30 years ago. And there's been many policy gradient algorithms are built on this idea. Now, when you're looking at this, you might still be concerned that if, from remembering back from the Monte Carlo methods we've covered, that this estimate G can often be pretty high variance. Okay. So in general, if you're just directly kind of averaging over sample returns, that might be high variance. So one of the next fixes we can do, and we'll get to this more on Wednesday, is to introduce a baseline. And let's see, I'll just say, so the goals here is that we're going to hopefully try to converge as quickly as possible to local optima. So we want to reduce the variance over our gradient estimate. And so the baseline is going to allow us to hopefully reduce, well, in general, yes, reduce the variance over this estimation process. And kind of we'll see two ideas next, which is introducing a baseline and then thinking about an alternative to Monte Carlo returns. So those are the ideas that we're going to go through next. I guess I'll just do one more thing, and we'll go through the proof of it next time. So I'll just introduce the concept of baseline, and then we'll prove it next time. So the idea in this case is that we're just going to subtract something off. And we're going to subtract something off that only depends on the state. This is only depends on the state. Okay, so this is not a function of your policy. Only depends on the state. And it will turn out, and we'll prove this next time, it's pretty elegant, that for any choice of something that only depends on your state, the gradient estimator is still unbiased. So you couldn't subtract off anything there that is only a function of your state, and you didn't change the bias of your estimator, which is kind of wild. And we'll prove that next time. But the goal is that we can hopefully reduce the variance of our estimated gradient by subtracting off the right thing. And just intuitively, the way to think about the baseline is that you don't necessarily just care about whether or not the gradient is positive or negative, and whether returns were good or bad. You might care about, like, well, how much better or worse are these returns compared to something else I could have done? Like, I want to know whether this policy A is better than policy B. And maybe both of them give you positive returns. One of them gives you 100, and one of them gives you 90. But you'd really like the one with 100. So you'd really like to move your policy parameters in the direction of stuff that is better than other alternatives. And that's kind of the idea of a baseline, is to say, like, well, maybe I know that I could probably always get like 90 for this particular state. How much better is this policy for this state compared to something I could do on average? And so we're going to sort of intuitively increase the log probability of an action proportionally to how much its returns were better than expected, where kind of the baseline is giving you that expected value. And we'll see formally on Wednesday how, by doing this with the baseline, it doesn't introduce any bias. So this is going to be one of the ways that we're going to get better gradients. The other thing that we're going to do on Wednesday is we're at least going to start talking about PPO, which is the second, which is a part of your homework too, bless you, which is going to involve more ways to kind of be more efficient and effective in the policy search we do. I'll see you then. Thanks.